Alright, so today I just wanted to finish up chapter 14 with you all, and what we were going through, let me get that off the screen, what we were going through is talking about reaction mechanisms. Now, as I mentioned in class, reaction mechanisms are something that's going to be extremely important as we kind of move forward into the next, let's say, phase of what you guys are going to be learning in chemistry. So when you guys get to organic chemistry, we're going to talk about reaction mechanisms pretty extensively at that point. But immediately, they have the purpose of kind of leading us into the next chunk of what we're going to learn for general chemistry also. So looking forward, the next couple of chapters, we're going to be dealing with something called equilibrium, and equilibrium is based off of kinetics, which is why every time every time we teach the second semester of chemistry, we always have to do kinetics before we talk about equilibrium. So what does that all mean for you guys? So what I'm trying to say is we're going to talk about this here, and it's probably going to seem a little bit complex, but we're not going to, I guess, get into the depth that we will see later on, is what it is. So it's one of these topics that is important. It's always kind of lingering in the background there, and if you're looking and if you're paying attention to it, you'll kind of see us kind of calling back the concepts here. But there are a couple of important things, and we did talk a little bit about them already in the previous class, but I just wanted to draw your attention again to the idea of a rate limiting step, right? And so if we're talking about a rate limiting step, this is the step that limits the rate. And whenever we're talking about rate, right, this is just how fast does a reaction proceed, right? So we're talking about the kinetics at this point. How fast does something happen? And so we're going to use this rate limiting step to be able to derive a rate law given a mechanistic set of steps. So the problems that come out of a reaction mechanism type of problem set, they look very similar to things like Hess's law, where we have an overall reaction and then we have a couple of, let's say, fundamental steps that we see that break down the overall reaction. And don't worry, we're going to look at an example towards the end of this video, and it'll make a little bit of sense. This is just one of those things where I'm going to sit here and I'm going to talk about it, and I'll do my normal brilliant, right? My normal brilliant attempt to make it all make sense, but it's really not until you sit down and look at a couple practice problems where it's all going to kind of come together here. So I do have to go, I am going to talk you guys through this stuff, and if you're kind of, zoning out or whatever it is here, then go work a couple practice problems, because that's really where it's going to kind of come together, okay? But the rate limiting step is the thing to pay attention to, and it's the slowest step of the mechanism itself. Now, when you take a look at these problems, you're going to see them labeled as fast or slow, and so we got to just find the ones that are slow and start to work off of that point right there, okay? If you're the slow step, you're several hundreds or thousand times or millions or whatever it might be slower than the other steps as part of the mechanism, so you're dictating the rate, right? It's like you're the bottleneck. And so if we're trying to derive a rate expression, then we need to find that slow step because it's going to kind of dominate everything, okay? So here's kind of a reaction mechanism here, right? We can see a set of steps where we have some kind of peroxide reacting with iodide ion, right, in the first step, and it ends up forming, some hydroxide and some kind of acid intermediate here, right? Now, what I mean by an intermediate is that this compound, the HOI, right, is immediately consumed in the next step here. So it doesn't linger to any appreciable amount, right? It doesn't stick around. And this is one of the challenges that we're going to have to kind of deal with. So remember, when we're writing some kind of generic rate expression, so if we have, rate equals whatever, K times A, times B, it doesn't, just as an example. Remember, A and B here are concentrations, and so we need to be able to measure those. And if we have an intermediate that gets formed and then is immediately consumed in the next step, it just doesn't linger around for us to be able to measure that, right? We can't put this into a UV device or whatever it might be, not device, a spectrometer, to be able to measure these. And so we can't get a rate expression if we have an intermediate as part of, excuse me, we can't calculate a rate if we have an intermediate as part of our rate expression. Here's what it is. So that's what we have to start to pay attention to. So when you guys are going through and starting to analyze these problems, what you need to do is take a look for things that are consumed and produced immediately in subsequent steps here, okay? The second thing to look for is, let's see, what color haven't I used here? We can do black. So if you take a look over here, well, let me erase that, right? We label this as the slow step, right? And if that's the slow step, then I can write my rate law down here for that K times the, this is the peroxide, right, H2O2, times the concentration of iodide. Okay. And it just so happens that if we have the right information, we can actually verify this, right? So we can go through, we can run a series of experiments by changing concentrations, and we can see if what we think is the rate law actually matches the observations for this, and it happens to be the case here also is what it is, okay? So a lot of important things on this slide here. We need to take a look at the slow step. We need to take a look at intermediates, what's consumed and, what's produced and consumed in the subsequent steps there, okay? So here's a typical look at a, let's say a problem to come out of this section of the textbook. So we have some kind of given reaction, right? 2NO as a gas plus bromine as a gas goes to make 2NOBr there, right? And it gives us information about the two steps as part of the mechanism. And we have a fast step and we have a slow step. Now, if we have the slow step, we can immediately go ahead and try and write a rate law. But what we see is that, right, we have this NOBr2 that's produced, and then it's immediately consumed in the next step here. And if we try and write our rate law, we see that our current rate law has that intermediate as part of its expression, which means we can't verify this in any way, right? There's no way for us to actually measure that concentration. If we go back and look, let's see here, I'll do this in red. The other part of our rate law has this nitrogen monoxide, right? Nitrogen monoxide. And so this is something that we can verify. This is one of the, let's say, the reactants that we need to get this reaction proceeding, right? So that is something that we can measure, right? So we don't have to worry about that because it is something that we can actually start this reaction with, so we don't have to worry about going through and trying to eliminate that as part of our rate expression. So it's only these intermediates that we see are produced and then consumed in subsequent steps here, okay? Now, remember, we're always paying attention to the fast and the slow here, right? So these are all the important parts again. So if we come across a situation where we have a rate law, that we have an intermediate as part of our expression, then we have to do some, let's just say, rearrangements to get rid of that. So let's take a look at how we can do that. Okay. So how we do this is we have to look at the rate limiting step, right? That's just a slow step, right? Here's the rate that we wrote on the previous slide there, so nothing different so far. Excuse me, I got a hair on my screen there. I have to move that out of the way. And like we said, it's an intermediate. We can't measure that, blah, 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 right? And down here at the bottom is what's going to help us out. The first step here is reversible, okay? And we can tell that by these double-headed arrows. Now, as soon as we get into the next chapter, we're going to learn a little bit more about what this kind of means for us. So just keep this in mind for now and just understand that, this is a reversible reaction, and that's going to have some meaning for us in a little bit, okay? The second thing to pay attention to is that this is fast, and this is going to be important also. So a couple of things here. Now, so we're going to have to use this fast reversible step to be able to rewrite our rate limiting reaction there. So here's what we're going to do. What we do, right? Let me get this out of the way here. Okay, what we're going to do is write a rate law for each side of this reaction. Okay. So if you want to pause, I know the answer's on the screen, but if you guys, cover it up real quick, right? So let's take a peek, right? If we just take this separately, right, we have rate equals K1, right? times the concentration of NO times the concentration of Br2, right? So we're just writing the rate in this direction, okay? And we can go in the opposite direction. Rate is equal to K minus 1, right, times the concentration of NOBr2, okay? Everybody with me on this? Right, we're just writing the rate in the directions. And rate is just equal to K times the concentration of your reactants in there, right? That's all it is. Now, at equilibrium, right, the forward and the reverse rate are equal, which means, right, that our black and yellow expressions there are equal to each other, right, because the rate forward has to be the rate backwards. That's just the definition of equilibrium. An important definition, right, and this is going to be something that's important for us as we move forward, okay? But here's the key part to this, right here, okay? So right now, essentially, so remember, let me back up for just a second. Remember that when we're dealing with chemistry, it's just a math game, right? The concentration of NOBr2 there is just a particular expression, right, that we can rearrange and solve and do whatever we need to with, right? This is just math. So what we're going to do is rewrite to be able to solve for the concentration of NOBr2, and this is what we get for that, right? So all we're doing is rearranging our equation, right? We divide by K, K minus 1 to solve for the concentration of NOBr2 here. Now what's important, right, or what's interesting about this and what we'll see is what's part of this here are the concentrations of materials that we can measure the concentration of, okay? That's not always going to be the case. Sometimes things are a little bit more complex, but we'll see what happens in certain situations, okay? But everybody with me on this? Let me kind of erase and clean it up for you guys here, right? So following along, what we did is we wrote the rate for the forward and the reverse reaction there. And then all we did is went through and solved for our intermediate, right? We solved for the concentration of the intermediate, which we can't measure directly, okay? So then we take that expression, right? We take that expression and we plop it right into this rate law that we wrote earlier, okay? So we just take the concentration of an NOBr2, and this is what we saw. Oh, careful, I shouldn't put that in square brackets there, right? This is what we had from the previous slide there, okay? And then we just simplify. We lump all our k's together, and we lump them into a new k, right? A constant times a constant divided by a constant is just a constant, right? So that's k prime usually. NO plus, excuse me, not NO plus NO. NO times NO gives us NO squared, right? And then we have Br2 here, okay? So this is what I was trying to mention earlier. So now, right, and let me zoom out here so you guys see everything. So essentially what we did is we just used math to rearrange to solve for the concentration of an intermediate given, right, concentrations of starting materials which we can check, right, which we can control, which we can measure. And so that's the key of how we solve these mechanisms. If we end up generating a rate law that has an intermediate as part of its expression, then what we have to do is find the equilibrium step or the previous steps and rearrange everything and solve everything to be able to generate an expression that contains only the starting materials which we can check against our experiments, okay? So this is an important slide here. This is stuff we've all talked about. Remember, we have a couple of defined things that we have to keep in mind, right? Elementary reactions are unimolecular or bimolecular, right? They can be written down from the stoichiometry, okay? So this is for an elementary reaction, which are usually the steps for a mechanism themselves, okay? And there's a couple other things to remember here also, right? But this is a good slide. I'm not going to read this out to you guys because I imagine you don't need to hear this in my voice, and you guys can always pause this. And it's in your book also here, right? But remember, these are kind of the ideas that we have for how we can solve these things and how we can work through them. Real quick, let's talk about what happens when we have a catalyst. So I think a catalyst is something that we're all familiar with, right? These are things we've talked about or heard about or discussed at some point, right? Especially if we're talking about biology and proteins and enzymes and these kind of things. But catalysts increase reaction rate without being consumed. So this is something important, right? A catalyst can't be consumed as part of the reaction mechanism or the reaction steps. So they need to exist at the beginning and at the end of the reaction, essentially. What is interesting and often forgotten or often ignored is that a catalyst actually changes the mechanism. Okay, so I mentioned this briefly the other day in class, but we're talking about something that changes the reaction profile diagram. And that kind of just changes the directions that a reaction needs to go, right? So if you have an uncatalyzed reaction, it has a certain pathway that it has to follow. If you add a catalyst, it has a completely different set of steps. So this is subtle but important. Okay. Now, how is this going to affect you guys? It's not really, but again, this is I'm setting this up for the next chapter here. Catalysis is going to come back when we talk about equilibrium and all these kind of things. Okay. What's important though is catalysts don't change the product and they don't change their relative proportions. And again, trust me, I'm just this is something that I'll call back to in the next. Oops. Sorry about that, everyone. This is something I'm going to call back to when we discuss equilibrium for the next few chapters here, okay? So a catalyst isn't going to change the relative proportions. So what's going on with this, right? If we're talking about something called an isomerization, which you don't have to worry about this too much, we're just talking about what side does this CH3 group kind of sit on. We'll talk about this a lot in organic chemistry when you guys get there, right? If we try and write a rate law for this, you see rate is equal to K times the cis-butene, and this is the cis-butene here, right? So typical rate law, rate is equal to some constant times the concentration of the starting material, right? It's a fairly slow reaction at room temperature, right? We can heat it up and start to change things and that kind of stuff. Or we can add a catalyst, okay? And then we can write a new expression for this, okay? And that's what we see down here at the bottom, right? And if we want to go through, we can actually break up what the individual mechanistic steps are. We see in the first step the iodine breaks down into what's known as an iodine radical here, and that radical does an addition to the alkene itself. And we'll learn about this actual flow of electrons next semester if you guys are taking organic chemistry, right? And we see it kind of go through a series of rotations. The iodine pops back off, and the I2 is regenerated at the end there, right? So why am I showing you all this? What does it matter? All I'm saying is that because we add that iodine, the mechanism is completely different. You don't see any of these radicals being generated, right? You won't see a radical generated if we are going through and doing this without the catalyst in there is what it is, all right? And so here's kind of a visualization of this. If you look at the pathway in green, that's with a catalyst. The pathway in red is just simply the rotation around the carbon-carbon double bond, right? So without the catalyst, the carbon-carbon double bond just rotates itself, which is difficult to do, right? You have to break bonds and make bonds and all this kind of stuff. So we have a completely different pathway, right? There's different hills and valleys in the green than there are in the red there. And that's what I mean by changes the reaction profile diagram, right? We have a different set of, let's say, instructions to get from one part to the other is what it is. I'm not going to read this out for you guys. This is the last slide that we have for this chapter here, right? This is just, what is a catalyst and, kind of the stuff that we're explaining there, okay? Now, before you guys go, let's take a look at a practice problem here. Let me tab over. Cool. All right. So here is a problem. If you guys want to pause real quick and see if you guys can solve this on your own. And see if you guys can come up with the rate law for the given reaction there, okay? All right, so let's take a peek at this. So it says, consider the following reaction, and it's given to you. That's nice. It says, here are the two steps, and what is the rate law, the rate expression for this particular part? Okay, so let's take a peek. First things first, right? We identify that. One more time. Here we go. We identify the fast versus the slow steps. Okay? The slow step is the rate limiting step. That's what we write our rate expression based off of. Right, so let's take a peek at this. Right, we would say rate is equal to K times O, right, times O3. All right, and we're done. Now, we wish, right, of course. So, all right, so we do this, right, we just write our generic rate law, and then we take a peek, right? So what we see here, gosh, this is there it is, okay? What we see is that we have this O that is generated and consumed in subsequent steps here, right? So this is an intermediate. So what we're going to have to do, right, what we're going to have to do is go and rewrite our rate expression for this, right? So let's just start to simplify things. I'm going to call this K2 here, right, because it's for the second step, right? This will just help us keep our K's all together. Oh, sorry, before I do that, let's take a peek, right? O3, right, is something that we add into this, so that's perfectly fine, right? So all we got to worry about is that O. All right, so let's go and write the rate laws for the fast step there. So we have, let's do this here, green. So we have K1 times O3, right? And that's equal to, let's do in black, K minus 1, O2, right? O. Everybody with me on this, right? So we have the K minus 1, right? And we have K1 there, right? So the forward versus the reverse reaction rate there for the fast. Now remember, our problem is this guy, which is right there. So let's solve everything. Let's just rearrange here. So let's see here. This is the concentration of O, and that's going to equal to, let's see, K1 over O3, right, divided by K minus 1 over O2. Right, so just divide by K minus 1 O2. And then I can take this expression into here. So let's see what that gives us. So I got rate equals K2. Then I got, let's see, K1 O3, right, over K minus 1 O2. And then I still have that O3 right here. Okay. Everybody with me so far? Right, just taking that concentration of O there and plugging it in. Let's make this look a little bit nicer. We can lump all of our, let's see, let's do that in green. We can take all of our K's together. So rate, we'll just call this green K, although we typically just call this K prime. The green K there is just fine. Alright, so we have O3, the concentration of O3 times the concentration of O3. So that's just ozone squared. Okay. And we've got over the concentration of O2. And that's just fine. That would be perfectly acceptable. If it was me, I would just write this as rate equals K1 O3 squared times the concentration of O2 to the minus 1 there, right? Just bring that up so we have kind of what we see as a typical rate expression there. Okay? Are we all good with this? Let's see. Do we have stuff that we can measure? Yep, we've got ozone, O3, and we got O2, and we can measure both of those things there, right? So that should be perfectly fine, right? Alright, so this is a typical step. So if you're able to solve through this, if you're able to get this, then it looks like you're on the right track. Just make sure you work one or two of these practice problems, and you will be all good. Alright, on Friday we'll continue working some problems, and then we will move on. Alright, I will see you guys then.